Okay, guys, final stretch here. So we're looking at finding the decay constant and the half-life. And at the end of the day here, we can go through here. And remember I've said 0 0.7 times the the half-life is when we get to the point where we're at 0 0.7 of the decay constant, or in this, so we set this when we want this capital N to equal 1/2 of n sub 0. If we do this algebra here, we can define tau as the half-life. So when the two of them are equal, then this becomes 1. And this is fun. There's nothing wrong with this, actually. But let's take a look here now. They tell us in the text here that lambda in the original formulation of e to the minus lambda t is going to end up being 0.182 when you have a chance that one out of 6 chance each time, and you would have expected it to be 0.1666. And yeah, this is the compound interest problem, and I should really have a supplement to this. So for the time being, since time is short, we're going to take my word for this, okay? So I could take this equation here, and so I can say that minus lambda t is equal to negative 0.693 and divided by tau. And the t is in there, so the t's cancel. So we end up with, since tau is under the divider line, we bring tau over to here, and we still have the 0.693. And then we bring the negative lambda, which of course, remember, is 0.1823. And if I do the division, I get a value for tau that I lost track of. And I'm writing all this on the wrong spreadsheet. I'm going to pause this. And in fact, I just did it here. 0.693 divided by 0.1823. Escape. And that's my expected value of the half-life. So in class, what I showed you was data when we had 300 dice. And I guess I'll have to pause while the boy is vacuuming. Oh yeah, I got interrupted by the vacuum cleaner. It's been a while, I forgot where I was. Alright, so the data I presented in class was where we had a 300 dice, and then we counted all the sixes and the not sixes, and I forgot to write it down how many sixes. So I tried to just reconstruct something that looked like what the data you guys got. So I just realized, I noticed there's the plot about here. It looks pretty good up to about here. At least what happened is, you see sometimes if I did a subtraction, I was getting negative numbers. But I got some nice looking stuff right here. And let's see, let's make these a little nicer looking. There we go. So the number of 6 is the square root. So you see error bars. And as I was saying, if I follow the lab manual, and so the lab manual says to draw a straight line through it, and then you have a certain number here, the y-intercept, and find the place where you get the halfway point, and then you, wherever that is on this line, you drop down and see what is the time. So I just set up a quickie straight line fit. The fit parameters are over here. And I made a chi-squared instead of a red squared because I have somewhat different size error bars, so I figured if I got them, I should use them. And then the clever part was that I said, okay, once I have the slope and the y-intercept, how do I figure out what is the value of x-axis that is at the halfway point? You know, instead of looking with my eyeball, I'm going to do it by math, right? So I'm basically saying that I have y equals mx plus b, right? So what I want to know then is that the value of x when y is equal to 1/2. So and already we have the y-intercept. Let's put the y-intercept there. Because we can be clever, because we know then that is the y at 1/2 of the y-intercepts. So it's y int over 2 equals the slope m times x, and you have y int here as well. So we have mx equals so that stays there, so, and this stays home as well, minus y int, and then we divide by the slope, the m, to get the value of x that I want. And so there it is. I goofed here, but I started writing it as the y-intercept first, minus y-intercept over 2. I was too lazy to redo it, so I just changed the signs. And what's nice is you notice that then the negative gets divided by a negative. And, you know, okay, sometimes we have to fudge it and say absolute value, but it's nice that it worked out. And then I went ahead and I used the value I got for lambda up here, and heck, I might as well make it, let's make it 693. Generally people just say 0.7. Oh, look at that. So notice how, heck, the one here using this was much better. Lambda, getting the lambda here was much better. And I suppose I could do a similar business there with the the half-life. But in your case, I wanted to just go over what you're supposed to get done. So this thing needs a little jazzing up. And you're done. It's not that big of a deal. It's much less of a big deal. Excuse me. Much less of a big deal than trying to fit with an exponential. I mean, some of us may yet do that, and that's fine. And in fact, strictly speaking, you would fit this with an exponential, but the error bars are so big compared to the difference, the delta y here, it would be a pretty ambiguous fit. Excuse me. and of course we could also do an r-squared fit here to check and see how good of a job we did as far as linear fit. That's what r-squared would tell us, but Oh, goodness of fit. I gotta remember if R squared will go for any curve. But even so, I mean, my calculated one and my measure from the large graph is amazing. And the one, and since, keep in mind that, let's see, we have 1, 2, 3, 4, 5, 6, 7, minus 2 parameters. We have 5 degrees of freedom, and divided by the sum of the chi-squared. Well, it's sum of the chi-squared divided by number of degrees of freedom. So it's less than 1. So it's not the best fit in the world, but that's all right. It's cool as hell. It works out so nicely just with dice. Okay, now I got to get this up on YouTube.